Hello everyone. Today I would like to talk about ESP8266 Wi-Fi module. This is quite cheap unit, it's about $1.40. So I have decided to buy a bunch of them. Each of these modules has LED integrated, which you can use for your own purposes, such as debugging or some custom indication. This unit also provides 8 independent GPIOs. They can be used for an external peripheral communication. Analog to digital converter is also available here. It's quite useful to make readings from conventional sensors. These shown standalone modules should have some additional peripheral in order to flash programs. By default, they do support flash using UART communication only. But we can make our life easier and just use completed development board. The price doesn't introduce any huge difference. The module which I use you can get for $2 approximately. You can consider it as a fully operational microcontroller like Arduino, but here additionally you will have Wi-Fi integrated as well. This configuration has the same amount of pins available, introducing almost no difference with previous unit which I just have shown to you. But if we'll take a look to the opposite side, then we can find some very useful components. This basically allows us to make UART communication over USB. As you can see, we have here CH340G chip. It will take care about all conversions between USB and serial protocols. This kit comes with a bunch of different pin headers, so you can choose any of them which will be suitable for your application. In my case, I have to find something simple and compatible with breadboard. These two pin headers looks quite suitable, so at the next stage we have to solder them to development board. In order to make perfect positioning while soldering, we can use breadboard as an alignment reference. Here we have our pins on a position. Let's place and align our PCB before soldering. I would recommend to use a flux paste. It's quite easy to clean even without isopropanol spirit. Just to secure PCB on a position, I will start with soldering of two pins which are located diagonally. Usually I apply flux paste using this small screwdriver, which I have found very convenient for me. We can supply some solder to our iron tip in advance, as long as we have flux paste in place already. Let's solder our pins. These two should be fine. So let's continue with the other pins. Now soldering is done and we have to clean up our flux paste. You can use dish cleaning liquid like Fairy or something similar, and toothbrush will be quite handy here. These are results after flux paste cleaning, so it should be fine for our application. Now let's connect our Wi-Fi module through USB port and let's see how can we compile and flash applications for this chip. Now I'm here in my Linux Debian terminal, so let's check which new USB devices we have. At this point you can see our USB to serial adapter, and we have to note its vendor ID and model ID for further configuration. Serial port access point we can find under /dev, And as you might notice, name will be assigned dynamically using numbered suffix. Also, default group for this file will be dlout, which we are not member of. So we would like to change it, and we would like to have some static name associated with serial port. For this purpose, we can create udevrules file. I will just use pre-existing template here. At the first part, we have a mask definition bound to all existing USB to serial devices. And at the next part, we define the vendor ID and the model ID, which we have noted previously. At the last step, we can define symbolic link name, which will be associated with our ESP Wi-Fi device. This would allow us to have a file name which will not change dynamically. Now we have to replug our USB device to see udevrules applied. Let's make a less-cell command against the USB TTA file. As you can see, group ownership has been changed to plugdev, which we are member of, so no issues with access rights. Also, you may notice that we have symbolic link created correctly, hence you can access ESP serial using predefined file name. In order to continue, you have to know exact ESP development board model. In my case, I just have bought one on AliExpress. You can easily find a bunch of manufacturers by typing ESP8266 in the search criteria. This one is a typical sample which I have bought. At the next step, you have to visit your manufacturer official website. In my case, this is a VMOS. I will just follow a link with my device name. At this page you can find quite a lot of useful information, such as flash memory size, operating voltage, and technical specification. Using this schematic you can understand what is the crystal frequency, LED connection schema, and other GPIO configuration. The next useful website which we'll need to visit is an Espressif.com. This is an official manufacturer of ESP chip itself. We have to go under SDK section and select Resources tab. Here you can find a bunch of useful documents and download links for SDK itself. We will use simplified SDK version without real-time operation system included. The link will redirect you to the GitHub project. At the bottom of the page you have to download tar.gzip archive. Alongside with native ESP SDK we will use Open SDK as well. So we will maintain two separate SDK versions, and I will create a common folder for them. Let me copy the archive and extract it here. We will need additional ESP Open SDK to compile and provide a toolchain, so it will allow us to build our applications locally without using additional virtual machine provided by Espressif. Let me remove the archive file which we have extracted already. And here we can check the content of native ESP SDK. At the next step we have to set up ESP tool which will allow you to flash applications into ESP chip. So first of all you have to make sure that Python is installed on your system. In my case I have version 2.7 in place already. We need to node Python executable full path. Then I have to install Python pip. This utility helps to download and set up different Python modules, and our ESP tool itself is represented as Python pip module. So let's use this pip to install ESP tool component. Once installed, we have to make sure where ESP tool main Python script is located. Usually you can find it at .local under your home folder. And we have to note down this script full path. Now I would like to show you some shell script template. This script allows you to trigger ESP tool to flash your binaries into the chip. You also can copy-paste this template from my website link, which you can find in the video description. As the first parameter, you have to set ESP serial symbolic link path. Then Python executable full path and ESP tool script location. And the final argument should represent bin folder location under ESP SDK. The next block makes basic check whether ESP USB to serial port is available. This command will make sure that all data will be erased before flashing. And the last section will trigger binaries flashing itself. So here we are just specifying our serial port parameter. Baud rate 57K is sufficient for my case. SPI flash frequency, which you can find in ESP documentation. It is also correlated with crystal frequency. And flash mode is specified according to your dev board requirements. The last part contains enumeration of partitions to flash with their corresponding offsets. We can find offset values from ESP SDK documentation. So this is ESP SDK Getting Started Guide. You can download this PDF document from the official Espressif.com website. On the flash map section, we can find two different ways how partitions can be flashed. Firmware over the air suggests having two separate partitions with support of dynamic updates. But we'll stick to the simplified version with a single user data partition. Table at download addresses section contains set of columns which are associated with SPI flash memory size. In my case, I have 4 MB memory chip, so I do pick up corresponding offset values. Another point which I have noticed in this documentation is the proposed way how the ESP compiler toolchain can be obtained. The official suggestion is to use VirtualBox and download image specified. And this is really disappointing for me. Why do I need to use VM with some Linux system embedded while I'm already running on Linux Debian? It might make sense for Windows users only to use virtual machine. On the Wikipedia page, I have found a solution to be able to build ESP applications locally without using virtual machine. So, as described here, ESP Open SDK allows you to build and use compiler toolchain locally. At the bottom of the page you can find a link to GitHub repository where this SDK is located. At the first step before compiling this toolchain, you have to make sure that all necessary dependencies are installed on your system. And this additional libtool bin package may also be required in your case. So let's make git clone of this repository. We have to make it under our dev-kits folder. Now we can see that we have one new SDK here. And to the next step we have to compile the toolchain using make with standalone option set to no. The reason why we need this option set to no is because we already have standalone native SDK. And the only one thing which we'll need from Open SDK is the compiler's toolchain. Compilation process has taken around 25 minutes for me, and now it is completed. Now you can check the following folder. It should contain our toolchain executable binaries. So we have to provide this folder to our path environment variable. I will do it by applying this path to bash.rc file. And you will need to restart bash shell once this file is modified. After restart, you can try to run compiler with version flag. In case of everything is correct, it should indicate build details. And now I can start with base folder creation for my Eclipse project. Let me call it simple ESP. Then I do create two additional subfolders. One of them will contain user module source files and another one include files. You can use peripheral test SDK example in order to pick up project makefile template. The same approach can be used for module makefile. Once folders with makefile templates are created, we can start our Eclipse IDE. Let me set up new workspace here. During project creation, you can select C makefile project with existing code. Then we have to pick up our project base folder which we have created before, and we can exclude C++. On the project properties, we have to make sure that makefile will be triggered with additional arguments. You can check descriptions and possible values for these arguments from the sample shell script below. The main idea here is that the same values should be used which we have selected previously in Flash firmware script template. And now we can review project's makefile template. The one point which I would like to mention here, that flavor parameter can be defined using conditional variable assignment with default value, instead of employing comments. The next two things which you will need to notice is a subject parameter and component lib file name. These two needs to be updated as long as you will decide to append additional module. Now we can review makefile for module itself. Here you can override default output library name as well. Inside projects include folder, you have to create new header file. You have to call it user-config to allow compiler to pick it up. We can keep default content of this header file which is generated by Eclipse. Now we can start with user main C file creation. This source code file will contain the main entry point to our application. In order to start here, we have to go back to ESP API reference documentation. We'll be interested in a function which registers system partitions. This function needs to be invoked in the first place. Here else you can refer parameter types. So the relevant header files needs to be included to be able to see these system functions. We will use osapi.h and userinterface.h. As you might notice here, Eclipse hasn't recognized these header files, so we have to make sure that we will append the relevant include folders to our Eclipse project settings. So at C language path and symbols section, we have to append SDK include folder. And additionally, we have to use include folder from our project's location. And one more setting needs to be appended to your Eclipse project configuration. This is the symbol which defines your device flash map configuration. You can look up this value from genmisc.sh compilation script which we have reviewed before. Now you can see that Eclipse has recognized our include header files. So we can start with the array definition which will contain enumeration of system partitions to be initialized. User interface header file can help us to understand which exact partitions are available. We have to look up the relevant enumeration. As you can see here, there are 3 mandatory partitions which needs to be defined at our application. So I will just copy paste these values here and will make sure that system partitions are properly defined. Each partition definition consists of unique identifier, address which can be calculated as you can see above, and lastly partition size which you can get from documentation. At the next step we have to define user pre-init method. It will be responsible to initialize our configured partitions. Then main initialization method can be defined, but before that we will need to specify which UART baud rate we will use. In my case 90,200 will be more than sufficient. here we are finalizing our user init definition. As you can see, we are using timer to trigger main run application method. The reason for that is just to make sure that hello world output will be printed after system startup messages. Now we are ready to create some makefile targets in order to compile our application. And I will start with creation of release target. We don't need to specify the target name here, as the default one will be used for compilation. And I have to append flavor command line argument to our build execution. It is the same parameter which we have reviewed before. Now we can trigger our build. As you can see, we have 0 errors, and at the next step we can check our output binary files, which are located on the SDK bin folder. So we have few Eagle image binary files which will be flashed from this location into chip memory. The similar way I will create makefile target to compile debug binaries. At the next step, we have to copy our shell script for image flashing into our projects folder. So let's refresh our Eclipse workspace, and here we can see our shell script which we were reviewing before. Our project's makefile also needs to be extended. We have to append 2 additional targets here. One of them will be used to clean image files. As you can see, remove command is used here. And another target is just to trigger image flash script. So once you will define your targets in makefile, there is need to append them into Eclipse project, and command line arguments are not required here. So let's save everything, and now I can trigger image cleanup. At the same time, I would like to create few more targets to clean temporary build files. So let's make them, and let's clean everything and rebuild everything from scratch. Once everything is built, we can trigger our image flash target. It will just execute our shell script which we have prepared before to flash application into ESP chip. And it will take some time to finish the step. While flashing the image, you will see main LED blinking on a module. And upon completion, you will see the verification results. In my case, it looks okay. Now I would like to start serial port terminal. I will use Minicom. It will allow me to see what's the ESP chip output. As arguments, we have to specify symbolic link to our USB to serial device and baud rate. Please note that baud rate should be the same as specified in application. So let's open our terminal, and we have to restart our chip to see the output. You can do it by clicking relevant button. As a result, you will see our hello world printed on the screen. So this is our first ESP8266 application completed. And here I have modified our example. Now it presents classic Blinkee application. At this version we have to initialize GPIOs in order to control LED. Timer initialization function is also adjusted to trigger handler repetitively. And the handler function itself is also updated to change the state of LED. This statement defines LED pin number, which you can find from ESP chip datasheet. So let's compile this version and see how does it works. And now our Blinkee application works fine. Now I have modified configuration here. I would like to use external LED as it will be much brighter. But 3.3 volts pin output with a small supported current will not be sufficient to drive this LED on a full brightness. So BJT transistor can be used as a driver. Base is connected through 1 kΩ resistor to GPIO pin. Additional 100 ohm resistor is used as a current limiting for LED. And here we have new version of our application. There is new function to process users' input commands. Each key presents specific action, so we can switch on and switch off LED, and using C key we can enter LED flashing mode. Run application method is also modified here. Now we have section to blink internal LED in a heartbeat mode. And the next block is responsible to read user's input. It will be received from ESP UART port buffer. And the last part will handle the external LED flashing mode. This LED will be controlled by 5th pin, which is initialized here. And now I will try to build it. As you can see, it is not successful. The reason for that is due to functions which works with UART buffer are not available in driver's library by default. And to fix it, we have to open uart.h file from driver lib folder. So let me try to modify it. So buffer enable directive should be set to 1. Once header file is saved, we can recompile driver's lib. And then our application itself. With new library it looks fine. And the next step I will flash it and let's see how does it works. All existing source code samples you can find on my website from the description below. As you can see, our integrated LED heartbeat logic is working fine here. Now let me open serial port terminal, and here we can make any input which will be passed directly to our application. Using special ABC characters we can control our external LED. Like here we can switch it on, either switch it off, either move it to the flash mode. So this is all for today's video. In the next video I will try to establish some wireless connections using this chip and make some useful applications. Thanks for watching. See you next time. Bye.